So now let's look at function notation. And so we use function notation in mathematics. It is common practice to denote functions by the letters such as lowercase f, lowercase g, capital letter F, capital letter G, and others. If lowercase f is a function, then each number x in the domain corresponding the corresponding number y in the range is designated by the symbol f parentheses x in parentheses. This f parentheses x, we read this as f of x. So a lot of times we will express our functions this way as f of x or g of x. And when you get further on in math, you won't even put in the x anymore. You'll just say f is equal to, and you'll assume that your variable is x, unless it tells you otherwise. So when a function is expressed in this way, we're using function notation. For a function, the variable x is called the independent variable. So our domain is the independent variable, our input, because it can be assigned any number from the domain. But the variable y is called the dependent variable. And this is because its value depends on x. So our output, y, is a dependent variable. Okay, so let's look at a function, and let's look at dealing with function notation. So for example, if you were given that f of x is equal to 3x squared plus 2x minus 4. So part A, we're wanting to find f of 0. So when you guys are going in and you're evaluating a function at a number or an expression, the best thing to first do is to go in and plug in parentheses wherever you see the x. So for our function in here, wherever I see an x, I'm going to replace it with a parentheses. So doing so, I would have the following. This is equal to f of 0, 3, I see an x, so put parentheses, squared, plus 2, I see an x here, so I'm going to put parentheses, minus 4. And so now all we're going to do is we're going to drop in the value of x. So this 0 is representing the x value of our point, and we're going to plug this in wherever we have our parentheses, which was where x was in our equation. So we can simplify this. Order of operations, exponents come before multiplication. So 0 squared is 0. 0 times 3 gives us back 3. I'm sorry, it gives us back 0. 0 times 3 is 0. Plus 0 minus 4. So f of 0 is equal to negative 4. So this represents a point here when x is 0. My y value is negative 4. So if we were looking at, just because I don't have room here, so part B, if I look at f of 1. So again, I'm going to go to my equation. Wherever I see an x, I'm going to put a parentheses. So I have 3 parentheses squared plus 2 parentheses minus 4. So dropping in the number that we're evaluating this function at, 1, wherever we sell the parentheses, and then using order of operations to simplify. So I have 1 squared first, which is 1. So I have 3 times 1 plus 2 times 1 is 2 minus 4. So 3 times 1 is 3 plus 2 minus 4. Well, 3 plus 2 is 5. 5 minus 4 is 1. So in this case, when x is 1, we get back a y value of 1. Part C, we're looking at f of negative 1. So again, you're going back into your function. Wherever you see an X, you're replacing that with just parentheses. And now go in and drop in the number you're evaluating inside the parentheses. Order of operations says that we need to square before we multiply. So -1 quantity squared is +1. -1 times -1 is 1. Plus 2 times -1, so this is really -2, -4. So I get 3 minus 2 minus 4, adding and subtracting in the order left to right. Add 3 minus 2 is 1, and 1 minus 4 gives us back -3. So here we have a point, -1, -3. So we're doing the exact same thing when it's telling us to plug in an expression. So in this case, part D says we're looking at f of -x. Do D up here. So f of -x. So again, we're going to go through and we're going to rewrite this. So we have parentheses wherever we saw an x. So 3 parentheses squared plus 2 parentheses minus 4. Drop in -x inside the parentheses, and then let's just simplify this as far as possible. So -x quantity squared, -x times -x is +x squared. I have 2 times -x, so -2x, and then -4. This is as far as I can take it. There are no longer any like terms, so there's no like terms in here, and so I can't simplify it any further. Part E says we want to look at negative of f of x. So we're taking -1, I can think of a -1 if that helps you to write it that way, all times our equation of f of x, which is this 3x squared plus 2x minus 4. So most common error that students make is they don't distribute that negative to every term for the function. They only distribute it to the first term. But that -1, and I don't have to put the 1 there, I could have just said this, and usually we don't. Just put a negative out front. It's like distributing -1 to each one of these terms. And so this would give us -3x squared minus 2x plus 4. So part F, we're looking at f of, so this time we're plugging in an expression. The expression in this case is x plus 1. So we want to plug that in wherever we see an x in our equation. So again, we're going to go through here. Wherever we see an x, we're going to put parentheses, but we're going to make it enough room to plug in x plus 1 inside those parentheses. So make that a little bit wider. So I have 3 parentheses squared plus 2 parentheses minus 4. So now drop in x plus 1 inside of our parentheses. This is where you need to be careful. I cannot distribute that 3 inside of that parentheses x plus 1 quantity squared because of that square. That x plus 1 quantity squared right in here, this is saying I'm taking x plus 1 times x plus 1. So it would be wrong if you told me that that was x squared plus 1 squared. That's not going to give me that result. Next piece, I want to distribute my 2 inside the parentheses. So I would have plus 2 times x plus 2 times 1 is 2. And then let's bring down our minus 4. So we want to simplify. So I'm going to distribute first my x plus 1 times x plus 1. But if you wanted to, you could distribute the 3 inside of just one of those parentheses, and then distribute that. But let's distribute x plus 1 times x plus 1. Doing so, well, we get x times x is x squared. I get x times 1 is 1x. I get 1 times x is 1x. And 1 times 1 gives me plus 1. So let's bring down the other pieces that we haven't done anything with. So plus 2x. I might as well combine 2 minus 4 right now, which is minus 2. So let's simplify inside of our parentheses over here. There are 2 like terms. There's no like term with the x squared, so I'm going to bring it down, but I have an x plus x. That's 1 plus 1, so that's 2x plus 1 plus 2x minus 2. Distribute our 3. So we have 3x squared plus 6x plus 3 plus 2x minus 2. So just combining like terms, and then we're done. So we have 3x squared. Here I have a 6x plus a 2x, and that gives me a 8x. And then I have a 3 minus 2. 3 minus 2 gives me plus 1. So f of x plus 1 gives us back 3x squared plus 8x plus 1. I am going to skip the last two, f of 2 of x and f of x plus h, because in a minute when we look at the difference quotient, we'll be looking at least this piece, f of x plus h. But you would go through and do the exact same thing that we were doing. Plug in parentheses wherever you saw an x, and then for g, you would plug in 2x wherever you had those parentheses and simplify. For part h, you would go in and plug in x plus h wherever you had those parentheses, wherever the x was in the function, and simplify. So earlier today in a different video, we looked at finding the domain given a set of ordered pair by giving a mapping. Now we're going to look at finding the domain of a function defined by an equation. So if you're given an equation and you're trying to find the domain, you're technically trying to find your trouble spots. What values of x would make your function undefined? Well, it depends on what our equation looks like. If you have a variable in the denominator, we can't divide by 0, so you have to exclude anything that sets our denominator equal 0. We can't have a negative underneath the square root and get back a real number. We saw that that was an imaginary number I, square root of -1, that was I. So we have to exclude any number that would give us a negative under an even-powered radical. When we get into logarithms, functions that are have logs in them, we also have to be careful. But right now we haven't talked about that, so you don't have to worry about those types of equations quite yet. But let me just read through what this states. It's a lot of what I just said, but we're just going to reiterate it in words through reading. So finding the domain of a function defined by an equation. Start with the domain as a set of all real numbers. So we're going to assume that the set of all real numbers is part of our domain. And then we're going to start excluding values. So if the equation has a denominator, exclude any numbers for which the denominator is 0. So trouble spot number 1 are numbers which set the denominator equals 0. So we got to exclude these values. The other part is if the equation has a radical with an even index, so like the square root, the 4th root, the 6th root, those are even index. The cubed root is not an even index. So if you have a radical with an even index, you're going to exclude any numbers for which the expression inside the radical, the expression underneath the radical is called the radicand, And we're going to exclude any number that gives us a negative underneath that radical. So another trouble spot is negative inside the radical. So those are the true trouble spots we're looking for given the equation. Okay, so we're given a list of equations and we want to find the domain for each equation. So again, we're going to assume that all real numbers are part of our domain, and then we're going to start excluding values. So our first example, we have f of x is equal to x squared plus 2. So I'm going to exclude any values which set my denominator equals 0. Well, notice there's no variable in my denominator. Technically, if I wanted to, I could write this over 1. So there's nothing that's going to set my denominator equals 0. So there's no trouble spot there. Or if this had a radical, which it doesn't, I'd have to worry about that. And so since there's no trouble spots for this equation, I would say that the domain in this case, well, there's a couple ways we can write this. Interval notation is negative infinity to infinity. We could do it set builder notation, x, the set, then x, vertical line such that x is contained. So that funky kind of capital E, rounded capital E symbol. And real numbers and capital R, that represents real numbers with 2 vertical lines. Is that part of capital? Is another way to do this. Okay, so that was for the first example. There was nothing we had to exclude. Our second example, though, we have f of x is equal to x plus 1. And that's all over 2x squared plus 8. So first going to assume that all real numbers are part of the domain. But now we're going to look for trouble spots and see if there are any. So notice that we do have a variable down here in our denominator. And so we're worried about when that whole denominator, 2x squared plus 8, is equal to 0. So let's solve for when that is equal to 0, if there is any value of x which sets that equal to 0. And then exclude them if we get something. Well, looking at this, if I solve for x, I could use my square root method because I have a perfect square in here. I could isolate my perfect square. So I have 2x squared. Subtract 8 on both sides of the equation. I get 2x squared equals negative 8. Isolating my x value, I could divide both sides by 2. So I get x squared is negative 4. Using the square root, square rooting both sides, I get x is equal to plus or minus the square root of negative 4. But recall that the square root of negative 1 was I, so x is equal to plus or minus. So this would give me back 2i. The value for x is not real. This is not a real number. So our domain is a set of all real numbers that we can plug in. So this is not a real number. So there's no real number that we have to exclude. So for our domain, for this function of f of x, again, all real numbers work. And so we could write that as negative infinity to infinity. Or set builder notation x such that x is contained in the real number system. So all of those values work. So the next example, we have capital G of x is equal to x plus 4 all over x cubed minus 4x. So again, I'm going to assume all real numbers are part of the solution set. Problem is that we do have a variable, multiple variables in this case, down in our denominator. And so we're worried about when is that denominator equal to 0? Is there any real number that would make that denominator equal 0? And so let's look at that. So we're looking at when is x cubed minus 4x equal to 0? Okay, so looking at this equation, I notice that I can solve this equation by factoring. So let's first pull out the greatest common factor from x cubed minus 4x. So what they both share in common in here is a single x. So I can pull out an x from x cubed, and I'm left with an x squared, minus pulling out an x from 4x, I'm just left with a 4. This is equal to 0. I notice that what's inside the parentheses, x squared minus 4, is a difference of square. So let's factor that. So bringing down the x that we factored out first, and then let's factor x squared minus 4. So difference of squares, that would be x minus 2, x plus 2 equals 0. So in this case, set each factor equal to 0 and solve for x. So we're looking at when is x equal to 0, when is x minus 2 equal to 0, and when is x plus 2 equal to 0. So x equals 0, x minus 2 equals 0, add 2 to both sides, we get x is 2. X plus 2 equals 0, subtract 2 on both sides, we get x is negative 2. So these are 3 values which set our denominator equal to 0. So these are 3 values that we have to exclude from the domain. Well, if you're thinking that on the number line, so technically at 0, I'm not including. At negative 2, I'm not including. And at 2, I'm not including. So I'm technically looking at everything coming in from negative infinity to negative 2. I don't want to include it, so recall that we use parentheses if we're not including that number, but getting really close to it. Union, then I'm hitting all the numbers, not including negative 2. So parentheses negative 2 to 0. Union, I'm hitting all the numbers greater than 0, but less than 2. So parentheses 0, comma 2. Union, so now I'm getting all the numbers that are greater than 2. So interval notation, I can write that as parentheses 2, comma to infinity. So this would be our domain of g of x in interval notation. And I could write this in set builder notation. One way I could do it is set curly bracket x vertical line such that x is contained in the real numbers, comma, but x cannot be 0, x cannot equal negative 2, and x cannot equal positive 2. So all numbers but those 3 numbers are part of our domain of capital G of x. The next example in here, we have f of x is equal to negative x in our numerator all over. In our denominator, we have the square root of negative x minus 1. So I notice there are a couple different trouble spots in this lower capital F of X. Or lowercase f of x. We have variable in the denominator, so I have to exclude numbers that set that denominator equal to 0. And then I also have an even powered radical, so I have a square root. So I need to be careful. I need to make sure that anything under that radical is a number, in this case, bigger than 0. So we cannot have 0 in the denominator. And we need what's underneath our radical, negative x minus 2. Normally, we could say greater than or equal to 0, but because this is in the denominator, it has to be strictly greater than 0. And so let's solve for x in this inequality. So I could add 2 to both sides. I get negative x is greater than 2. To get x by itself, recall if we divide by a negative or multiply by a negative, that flips our inequality sign. So dividing by -1, I get x is less than 2 divided by -1 is -2. So any number that I plug in that is less than -2 would give me a positive number underneath that radical. And so this is our domain. X is greater than -2. Interval notation, we'd have -infinity to -2 parentheses. Or we could write it self-folder notation, x vertical line, such that x is less than -2. So equations, when we see equations, they can either be written in what we call implicit form or explicit form. So in general, when a function f is defined by an equation in x and y, we say that the function f is given implicitly. If it is possible to solve the equation for y in terms of x, then we can write the equation and say the function is given explicitly. So for example, let's say we had 2x plus y is equal to 6. This equation is in implicit form. Notice that we have both x and y on one side of the equation. I noticed that I could take this equation and I could write it in explicit form by solving for y. So I could get y by itself in that equation by subtracting 2x. So the explicit form of this equation would be y is equal to -2x plus 6. So another example of an explicit form, what if we had y divided by x is equal to 1? So this would be an implicit form. Explicit form, sometimes it's impossible to change our equation that's in implicit form into explicit form, but in this case I could. By multiplying both sides by my variable x, I get y is equal to 1 times x, or x. So that would be the explicit form of that equation. In this case, technically x could not be 0. Actually, both cases. So if you have x and y on both sides of the equation, together on one side of the equation, then it's an implicit form. If you have your function y by itself, no y on the other side, then it's an explicit form. Okay, so we did not finish this chapter or this section yet. We still need to look at finding the difference quotient and operations of functions and finding the domain of the operations of functions. So we'll finish that piece up on the next lecture.